Okay, thank you for the kind introduction. Um, so in this presentation, I will talk about the roadmap for extreme scale simulations, and in particular on the evolution of Poisson solvers. Just to clarify from the beginning, I will not present any new algorithm about solving Poisson equation, but instead of that, I'm trying to analyze how the complexity of solving Poisson equation is going to increase when we go to higher and higher Reynolds number, and therefore finer and finer breeds. Okay, so we will see that there are two competing effects. On one side, we have finer and finer breeds, therefore the linear system of equations is growing. So in that side, it makes the system more complex, but also the time scales are getting smaller, and this we'll see that it may benefit the Poisson's solution. Okay, so just quickly, well, this is a plot that you have seen many times already in this conference. So we have an exponential growth in the computational capacity. Therefore, sooner or later, we'll be able to solve bigger and bigger and bigger cases. Okay, so we can just make some extrapolations just for fun of at what point we will reach, well, we already reached X, but Z scale. For CFD applications, probably it's more relevant to look at the HPCG because it's a sparsely algebra. Okay, but well, in any case, it will sooner or later it will go to routine CFD simulations to be able to run really huge meshes. So what we want to address in this presentation is this question, as I said before, whether the solving Poisson equation will get either more difficult or less difficult to be solved when we go to larger and larger Reynolds numbers. So just a quick reminder, I guess everybody already knows, but I think it's interesting to remind a little bit and also to fix some notation. Okay, so Poisson equation, it arises from the solution of Navier-Stokes equations for incompressible flows. So basically, I just explained the idea of a very simple fractional step algorithm. So we solve momentum equation. In this case, we can explicit the scheme, but it's not relevant in this point. We get some predictor velocity in blue. Okay, this predictor velocity is not divergence free. And then we need to solve a Poisson equation. Okay, and from that Poisson equation, we get a pressure field for the next step. And we use that pressure field to project the velocity field back into the space of divergence functions. Okay, so solving Poisson equation is the most time-consuming part of any compressible solver. And also it's the most difficult part to parallelize. So let's start looking at more detail at this equation. Okay, so if we increase Reynolds number, what we will see is that basically we need finer breeds, and therefore more grid points. Therefore, we have larger grid systems equations, and this will, of course, not basically will increase the complexity of solving the Poisson equation. But on the other hand, we will see that also the time scales get smaller, and this will lead to better initial guess that also has a beneficial effect for the convergence of the solver, assuming that we are using an iterative solver like multi-grid, for instance. Okay, so every time we increase Reynolds number, in this case prime number, we need finer grids. Okay, so but how fine these grids are getting? So to answer that question, we have the classical theory. So from this slide, the most relevant is just to remind that the Kolmogorov left scale decreases with Reynolds power minus 3/4. And also from the classical Kolmogorov theory, we know that the smallest time scale decreases with Reynolds power minus 1/2. This is what the physics is telling us. From a numerical point of view, we also have the CFL condition that restricts a time step when we're using explicit time integration schemes. For the convective term, we can find that the time step decreases with Reynolds power minus 3/4. And for the diffusive term, if we would use an explicit scheme, it will decrease with Reynolds power minus 1/2. Okay, so in summary, what we have is at the end, it's the grid size decreases with Reynolds as expected with minus 3/4. This is from Kolmogorov theory, and the time step also decreases with time step with Reynolds power alpha, where alpha is basically either 1/2 or minus 3/4. Okay, so probably will be minus 3/4 because it's the most precipitated condition. Okay, so let's go back to the Poisson equation. Okay, so on the left side, we have the Laplacian operation. On the right hand side, what we have is the divergence of the predictor velocity. So if we want to analyze the convergence of the solver, we need information regarding the initial residual. Okay, so this is the initial residual. We'll be basically assuming that the initial guess of our solver is a pressure from the previous time step. Will be the difference between the Laplacian of this pressure minus the right-hand side of our equation. Okay, and the Laplacian of the pressure of previous time step is indeed assuming that in the previous time step we solved the Poisson equation as well. It's equal to the divergence of the predicted velocity at the previous time step. So basically, what we see is that the residual is almost the same as the partial derivative on time of the divergence of the predicted velocity. We could define the residual in a slightly different way. Basically, the only difference between this equation and this one is that I'm multiplying both sides of the equation by the time step. Probably this criteria is more meaningful from a physical point of view because the residual is directly related with the error in our divergence free condition, the velocity. So in any case, the reasoning is exactly the same, and what we find at the end is that the residual is proportional to the time derivative of the divergence of the predicted velocity. Okay, so let's look at what is the divergence of the predicted velocity. So predicted velocity, remember, it comes from the solution or advancing on time momentum equation. Okay, so because the flow is incompressible, many terms they will cancel out, and the only one that contributes to this term, to the divergence of the predicted velocity, is the divergence of the convective term. And the divergence of the convective term is equal to the second invariant, Q invariant of the gradient velocity. Actually, this is well known, I guess, for everybody, because it's a typical criterion, which was this Q criterion to visualize vortex structures in the world. So this is the formula of the invariant. We will also use another invariant, which is invariant R, which is the third invariant of this gradient tensor. Okay, so basically what we have at this moment is that the residual of the initial residual of the solver will be proportional to the partial derivative of the second invariant. Okay, so we will see that assuming that the flow is incompressible, inviscid, and no pressure effects, we have what's called restricted order equations that describe an exact relation between the time evolution of these three variants, invariant U and invariant R. Okay, so assuming that this relation is valid, at least for some range of scales, okay, we could approximate the residual in this way. So basically, I'm just applying this equation in X. Okay, so in summary, what we have is the residual is proportional to the time derivative of the second invariant, which we may assume that it's equal to this. Okay, and also there is a delta D factor where with a P exponent that depends on the criteria that we use for the residual. Basically, most likely will be equal to 2. And then as I said before, the time step decreases with the Reynolds number with these exponential relations, and the grid size as well with a minus classical minus 3/4. Okay, so if now I will make an hypothesis and will assume that this in the Fourier space, this partial derivative of the second invariant scales in this way, where beta is the exponent that is not known yet. Okay, I assume that there is this kind of relation, at least for some inertial range. Okay, and combining all these things together, basically what we found is that the initial residual in the Fourier space, it has a Reynolds dependence. Okay, where alpha is basically the product of this P times the alpha that comes from here. Okay, so this is comes from physical reasonings and combined with numerical reasonings, and then there is this wave number of dependence with this exponent beta that we don't know yet. So for the evaluation of solver conversions, we will need to do some estimations of the L norm of the residuals. Here we can make use of a Parseval theorem that basically is telling that the L norm of the residual in both physical and Fourier space is the same. Okay, so from that we can easily study the conversions of the solver. I just studied firstly a Jacobi solver, which is the easiest to study. And we find a very interesting results. Okay, let's just skip some of the steps. Okay, the arithmetics are relatively easy. So what we see is that the conversions of the solver, N is here it's iteration number inside the Jacobi solver. Okay, it converges in this way. It's proportional to this. There is some constant in front, but what is important is a Reynolds dependence, which has this exponent on the top. Okay, but you may argue at this moment that Chekhov solver is not a solver that we want to use because it's not efficient. Okay, but we can extend the analysis for multigrid, assuming that we use Chekhov as a smoother for every multigrid level. Okay, and basically the multigrid converges much faster because there is this factor here that accelerates a lot the convergence. But now I'm not interested in this, but I'm interested in the fact that the prefactor is exactly the same and has the same Reynolds number dependence. Okay, so basically this is the result that we find, at least for Jacobi multigrid solvers. So the convergence has this Reynolds number dependence. So basically, if you want to know whether the number of iterations to reach convergence will increase or decrease, we only have to look at the value at the sign of this exponent. So if this exponent is positive, we are in this part of this two-dimensional fixed state diagram, okay, meaning that the number of iterations will increase with Reynolds number. And if we are in this side, it will mean that it will decrease. So solving the Poisson equation will get easier. Okay, so in practice, as I said before, probably we will have values of people too, and values of alpha minus 3 halves, so will be somewhere here in this line. So it means that if beta is larger than 7.6, we expect that solving the Poisson equation will get more and more difficult. If it's below that, we expect that it will get easier. Okay, so but we don't know yet this value of beta, or even if there is this inertial range for this quantity, which is the partial derivative of the second invariant of the gradient tensor. Let's see the gradient tensor. Okay, okay, so basically this is basically the old underlying idea. Okay, so this is initial residual distribution in the free space. Increasing Reynolds number makes the spectrum wider and wider because we have a wider range of scales, but also the effect of time step increasing moves this a little bit down. So basically at the end, it will be the key point is to determine which is a slope, okay? Because the slope will determine whether it's getting more or less difficult from when we increase Reynolds number. Okay, so what do we know from the classical theory? Okay, we know, of course, the Kolmogorov energy spectrum. Okay, so we have this classical minus Striker dependence. This is for the kinetic energy distribution among different wave numbers. Okay, the results correspond to the NS data extracted from the Johns Hopkins University database. Okay, of course, we observe this minus Striker spectrum, no surprise so far. When we move to pressure, the prediction is that it should scale with minus 7.6. Okay, this is also what we are observing at this moment. Okay, more interesting things. The second invariant Q. Okay, actually we can derive the right scaling of this invariant. No, recalling this relation. Okay, the Q invariant is in the right-hand side of the Poisson equation. Okay, therefore we can find out the relation of the exponent for the second invariant from the external pressure. Okay, so because basically we have here a second derivative, so basically it's adding a factor of 2 and getting the right exponent for the second invariant. And actually this is what we see also from the DNS data. Okay, third invariant, we can also derive the exponent that also it's well observed in the DNS data. And then finally, how it scales this partial derivative of the second invariant. Actually, what we observe is a very interesting result. Okay, firstly, we observe in this range of intermediate scales an 11.6 exponential. Okay, and then for larger scales, we observe 5.6. Okay, so basically, we can explain this 11.6 from this term, which is the convective term. So it's how the second invariant is being transported by the velocity field. Okay, basically assuming using a Taylor-Frozen hypothesis. And so basically here you have the derivative of the invariant. So basically just adding 1 to the exponent is 5.6 plus 1, you have this 11.6. Okay, so this is nice to explain this behavior here. here we have the second term, which is a 13 variant. The 13 variant doesn't have this 5-6 slope, so it's not explaining this behavior here. But if you remember this equation, basically it's a simplified model. It's a Euler equation. The exact equation has two additional terms. One comes from the pressure contribution, and another comes from the viscous effects. Pressure contribution is given by the trace of the gradient of the velocity field multiplied by the Hessian of pressure. Okay, it's a little bit complicated to derive, but it's what we see here is when we analyze this term from the database, that it exactly fits with this 5-6. Okay, so we can physically explain these two different regions. But the most interesting is at the end we are observing this 11-6 in slope for intermediate skills. Okay, so to conclude my talk, we have identified two competing effects on the convergence of Poisson equation. Okay, so based on that, we have defined a phase space that divides into regions depending on the solver convergence. So here it gets more difficult, and here it gets easier. So what we saw at the end from the theory developed and also from the analysis of the NS data, that at the end it seems that this exponent beta it's 11.6, so it means that we will be clearly in a region where the solver gets more and more difficult. But from the theory, apart from knowing that it will get more and more difficult, and therefore we need better and better preconditioners, it's also a way to develop or to find some ideas regarding how complex it will be to solve Poisson equation for finite and finite things. Okay, and finally, ongoing research. These are results for a relatively low rain loss lambda. We are extending it nowadays for analyzing data for much larger meshes. And also we want to extend this analysis for more complex solves. But at this moment, everything was homogeneous isotropic turbulence, but we want to study also if this is also applicable for more complex configurations. Okay, thank you very much for your attention. If you have any question, I'm with